Okay, so let us start the discussion for today. So, hello everyone, my name is Rajiv, and today we will be discussing about the week 3 lectures of the NPTEL Introductory Field Structural Geology course. And so, today I will be discussing mostly about a specific topic that has been taught in the lectures, especially the final lecture of week 3, which is regarding the strain analysis of deformed samples or deformed rocks that we commonly find in the exposures of while we are conducting the field work. So strain analysis and the practical methods of strain analysis is a very important tool for structural geologists, through which we can quantify, not only to qualitatively analyze the different strain conditions, whether it is a plane strain or it is an axially symmetric strain, or flattening or stretching, whatever kinds of different strains we get, whether it is a pure shear or simple shear or subsimple shear. So these all kinds of strain we commonly encounter in the field, and not only to qualitatively analyze the data to get the idea about the overall shear sense of the region, but also we can actually quantify the amount or the magnitude of strain, whether it is a pure shear or simple shear. We can actually quantify that, and to quantify the strain directly from the field evidences, that is deformed rocks, deformed strain markers, different fossils, even from microscale or observing the microstructures from thin sections. So there are a lot of various ways we can actually quantify the amount of strain that has taken place. So, in this discussion session, we will mainly focus on the different practical methods that we commonly apply while analyzing the strain to understand the deformation kinematics, as well as to identify different domains of strain, and from which we can actually have further implications about the regional deformation of an area. So, let me share my screen. Okay, so point of discussion. So today we will mainly talk about 1D, that is one dimensional, two dimensional, and three dimensional strain analysis. So in the lecture, you have been specifically taught about the use of Flynn diagram. But Flynn diagram is one of the tools that we commonly apply for analyzing three-dimensional strain. But there are two other kinds of deformation, that is 1D strain as well as 2D strain. So we will thoroughly go through the different applied methods that we commonly apply, different statistical methods, different geometrical methods, and we will uh, study four of such specific strain analysis methods. Okay, so the discussion mainly will cover so we will today discuss about strain markers, Okay. And then I mean the how we identify different strain markers and what are their utilities, and then we will study one dimensional strain analysis. So we will discuss two methods regarding one dimensional strain analysis. Then we will finally we will discuss two dimensional strain analysis, and here we will also discuss two commonly used methods, which are, one is Fry method or center to center method, and the other one is RF phi method. So we will elaborately discuss these different strain analysis methods and their theoretical background and how to perform step by step, performing these practical exercises. And finally, we will touch upon the three-dimensional strain analysis, which we will also discuss about the Flynn diagram. So in structural geological field work, this strain analysis is a very important part. So wherever you are doing a field work in a deformed terrain, in that case, having a robust idea about the collection of different deformed data, I mean, well, it can be linear data, planar data, and also some aspect ratios of different deformed strain markers. So different kinds of things can be utilized. And we will also, I mean, these methods are also helpful not only to understand the strain distribution, but it also tells us that in a constrained setting where the tectonic forces, they remain constant over a period of time, the strain is accommodated differently in different objects. So in a same assemblage, if we have a stiffer material, it will deform less, whereas a material which is soft and ductile, it will deform more, and it will rather show a flow nature. And in that case, we will have a very large amount of strain accommodated through that kind of materials. So this fact is known as strain partitioning, and strain partitioning is essentially important while we study different microstructures, and from that we identify the rheology of different mineral phases, say for example quartz or K feldspar or plagioclase feldspar. So these are the common constituents of the different rocks that we commonly encounter, whether it is an igneous rock or sedimentary rock or even metamorphic rock. So in all of these rocks we see distinct strain partitionings, strain localization. So these are the terms you would commonly encounter while uh, working on crystal plastic deformation of rocks. And in that case, having a good sense about the strain distribution and the kinematics of different strain markers would help you to understand how strain partitioning has took place, right? So we will start with uh, the strain markers. So what is a strain marker, right? So say for example, you are conducting an experiment, right? So you have a square or rectangle like this, and you have applied simple shear on that object, and after a considerable amount of shearing, you see that the shape has been transformed to somewhat like this, right? So this transformation, simple shear transformation, tells you about the evolution of the shape. So we estimate the strain from the geometric evolution of the subject, right? Now, what is the subject in this case? This is the square or the rectangle from the initial position. So in order to quantify the strain, you must know the initial shape, right? So from there, you can actually have an idea about how much shear strain has been accommodated, right? So then you can apply the classical formula. So if this is theta, then gamma is simply tan theta, and from there you can have an estimate of the shear strain, the magnitude. But in order to calculate this magnitude, you need the initial shape of the object. The same thing can be also done while applying pure shear, right? So if I apply pure shear deformation to this object, what would happen? So it would become like this, right? Even though in that case we need the initial shape to estimate how much strain has been accommodated through simple through pure shear. So this is the compaction and this is the dilation, and in this case this is the rotation or the shearing direction. Right? So the point is that while you are doing an experiment, whether it is a simple shear or pure shear, in experimental condition you always know what is the initial shape of the object or the initial geometry of the subject that is being deformed. But in nature, while you're observing deformed rock samples, we don't actually have the idea about the initial shape of the objects that we are trying to understand. Say, for example, you have seen a quartz ribbon in the field. It is very likely to form or to encounter a quartz ribbon. Even it can be in microscopic scale, or you can also observe that in microstructure. So whatever it may be, you think that you found a quartz ribbon, and you interpret that thing that this has must been stretched, and that is why it has formed. But you never know how much stretch has taken place on that quartz ribbon unless you know what is the initial shape of the quartz grains that coagulated with each other, and then it formed this ribbon through crystal plastic deformation mechanisms. So unless you have an idea of the initial shape of an object, you cannot comment whether the object has undergone pure shear or simple shear, and furthermore you cannot also comment how much strain that object has accommodated. So in order to reliably estimate the strain, whether it is simple shear or pure shear, I mean the nature as well as the magnitude of strain, we need some markers. So markers are basically some objects with defined initial geometry. So anything, any object familiar to us which has a very specific geometry in the undeformed state, we can use that kind of object as the reference, and from that we can actually estimate how much strain that object undergone straining has been undergone through this object, and eventually we can have an estimation of the amount of strain. So in that case, these strain markers comes very handy. So I can write that strain markers are natural objects with well defined, undeformed, or initial geometry, which can be utilized to estimate the strain accommodated by a deformed particle or object in a rock assemblage, right? So this is the utility of strain markers. Now there can be, ideally there can be 6 different kinds of strain markers, so we can list them one by one. So number 1 is original. Let me write it in different color. So number 1 is original spherical or equidimensional form. So any object with original spherical or equidimension means it is euhedral in nature. The shape is euhedral in nature. So examples are ooids. These are limestone concretions that we generally observe in limestones. These are made of different calcite and aragonite interlayers, and these are spherical in shape. Also reduction spot, some microfossils like foramina and radiolaria. These are microfossils. Mineral aggregates in Hornfelsic igneous rock. So this is a kind of strain marker. Okay, number two is original circular cross section on a known surface. Okay, so in this case the ideal example could be pebbles in sedimentary units, then rain imprint structure, also syn sedimentary deformations like convolutes. Right, and some ichnofossils like the wormholes or ant burrows, these kind of things, some ichnofossils. Okay, so these are the examples of some original cross section, I mean circular cross section observed in original uh, surfaces of or rather known surfaces, right? Okay, number three is it is original non-spherical original non-spherical objects. Now original non-spherical shape could be anything, right? So anything that is not spherical could be non-spherical, but in that case we approximate an elliptical shape over the object or the strain marker which we are interested about, right? So original non-spherical objects, in that case we approximate as ellipses. Approximating elliptical shape. So in that case examples would be pebbles and conglomerates, and ooids in sedimentary unit. Okay. Then number 4 is original linear form. Okay. So original linear forms can be different fossils, cross stratifications, etc. Number 5 is bilaterally symmetrical objects. So bilaterally symmetrical objects are generally fossils like brachiopods or bivalves. These are bilaterally symmetrical, and we use these deformed fossils as markers to quantify and analyze the different amount of strain and nature of the strain. So these are brachiopods, trilobites, right? And echinodermata fossils. And finally, number 6 is known initial angles. In that case, we generally consider cross beddings and mud cracks. In microstructure, we generally consider euhedral, rather prismatic crystals, minerals like quartz. Okay, so these are the 6 different kinds of strain markers. So these are ideal strain markers. Availability of these things can help us to estimate the amount of strain that has taken place in an area, right? Now we will further study different types of strain strain analysis: one dimensional, two dimensional, and three dimensional. So let us start with one dimensional strain analysis. So let me quickly show you a picture. So see this image. So this image, it is a fossil. Okay, and this is known as belemnite fossil. So this is deformed belemnite. Now belemnites are test tube shaped gastropods like this. So these are the shapes of these belemnites. It is a strain marker, right? Because it has a very specific geometry, right? And we mostly consider, because the cross sectional dimension is less than its transverse dimension or length. Length is very greater than width. So in that sense, we consider this as a linear marker, right? Linear marker doesn't mean that the object has to be one dimensional. In practical senses, we consider, since the length of the object is very much greater than the width itself, therefore we consider it as a linear marker. And in case of belemnite, the initial shape is very well constrained. How do we constrain initial shape? Because you also get some undeformed fossils. So you can search in the internet to see about belemnite fossils, and you will see a plenty of fossils. These very sharp teeth-like objects. They often it looks like a teeth of a or tooth of a dinosaur. So that kind of thing, the belemnite. But actually, it is not like that. It is even a gastropod. It is the exoskeleton of that gastropod. It remains as a fossil, and when the entire rock is being stretched, the belemnite, being a stiffer material, it is fragmented into different parts. So we can see that these are the different fragments. So this is one fragment, this is another fragment, this is another fragment, right? And so on. So these are the different fragments of the belemnite. Okay. And in between we have secondary mineralization. Okay. So these are stretched and fragmented. And in between that, the rock matrix has been introduced like this. So you can easily say that this is the stretching direction along which the belemnite has been pulled apart, and this is the compression direction. And because of that compression, the rock matrix has filled up the gaps between these belemnite fragments. And from that, we can actually estimate how much strain has been accommodated through these deformed belemnites. Okay. So this is a demonstration of one dimensional strain, where it is simply being pulled apart and the fossil has been fragmented into various parts. So now we will go into our theoretical part, where we will discuss about the different theoretical basis for estimating, for actually practically estimating the strain accommodated through the deformed belemnites. Okay. So we will discuss about two methods. So the first method was proposed by Ramsay, 1967, and the other one is Hossein's method, which was proposed in 1979. Okay, so we will discuss these methods briefly about how this strain estimation is done. So let us consider about Ramsay's method. So how the deformation happened? So if we consider, sorry, so consider this as the initial belemnite fossil. Initial, okay. So this is the undeformed belemnite, or we can say any one-dimensional marker, right? Now what we are doing is that we are applying a stretching in this direction. So automatically it will be compressed along this direction, and as a result it would be fragmented into multiple parts, right? Okay, so this is a schematic representation of this. So these are clearly not to scale, right? I'm just showing how it is being theorized. So now we are seeing that there are fragments. So these are fragments, right? And this is the gap space in between the fragments, right? So there are fragment lengths as well as gap length. So we consider in Ramsay's method the fragment length, which is represented as F, and the gap length, which is represented as G. Okay, so if there are n number of gaps, then there will be n plus 1 number of fragments. This is a very simple mathematical estimation. So if there are n gaps, then there will be n plus 1 number of fragments. Uh, Anybody speaking? Kindly mute yourself if you are not have any question. Okay, thank you. Okay, so if there are n number of gaps, then there will be n plus 1 number of fragments, and mathematically the uh, formulation for Ramsey's method is G total, that is the total gap length, is the summation of I equal to 1 to n gi, and F total is basically summation I 1 to n plus 1 Fi. So where gi and the Fi are the individual gap and the fragment length okay. So this is how we actually calculate the total gap length and the uh, fragment length. Now, so before deformation, before deformation, the initial length would be F total, because if we assume that the fragments itself are not stretched and they are remaining as rigid objects, so therefore by just adding the total length of these fragments, how many fragments are there, if there are n fragments, and if each of them fragment has a length of F, so say for example equal length, then we simply have to add the total different length of these fragments, and from that we get the initial length of the undeformed sample. So in that case the undeformed sample would be unfragmented sample. That means that the total length of the fragments is the initial length of the, or the initial dimension of the fossil. After deformation, the final length would be, you can guess it, G total plus F total, because now there are gaps in between where the rock matrix has been introduced, and now it has extended the length further away. So So the final length would be G total plus F total. So now if we are to calculate the stretch, stretch S, we would simply have final length by the initial length, right? So that means we will have F total plus G total divided by F total. So that means we will have 1 plus G total plus F total, right? Now this is, sorry, now this quantity, this is known as the elongation. So the relation between, or this is rather simply the strain, right? The relation between S and E therefore is S is equal to 1 plus E. Okay, so this is a mathematical relation, and from that, once we have this S or the amount of stretch, we can also calculate the quadratic elongation. Quadratic elongation is denoted by lambda, which is simply the square of the stretch amount. Okay, so it is very easy to perform the Ramsay's method. We just simply need to calculate the individual gap lengths and the individual fragment lengths, and eventually we can calculate G total and F total, and then by using the different formulas we can estimate how much strain or elongation, how much stretch, and the quadratic elongation has been accommodated through that deformed belemnite or the deformed one-dimensional marker. Now coming to the Hosen's method. So this method seems very perfect, right? So there is no flaw apparently, although there are some, these are very crude mathematical estimations for calculating the strain, but for an overall initial idea, at least at the field, we can have these kind of methods to estimate the rough estimation of what is the strain accommodated through these deformed markers. Now the case is that in the photograph you can eventually see that the end part of the fragments are not properly preserved. Fragile end parts. So this is a very critical thing. The end parts are of not often been preserved exactly. They can be fragmented into several other pieces. Even they can be cataclysized. That means they are reduced in the size. They can be pulverized, or they even can be vanished from that outcrop that you are observing. So while it is being fragmented into many parts, or even that the fragments can rotate as well, not necessarily this entire thing has to be linear, right? It can rotate. So eventually there can be a lot of complications uh, during the deformation process, and that can eventually lead to fragmented and pulverized uh, end fragments, or the end parts especially, and that can create a problem. In that case, how can you measure the length of those fragments at the end parts? So the Ramses method tells that you have to take the length of each and individual fragment lengths. So in that case, the Hosen's method comes to very handy, because it estimates that, or it tells that you should not take the entire length of these end fragments. So now if I elaborate the Hosen's method, so I'm just drawing the deformed markers. Okay, so Hosen's method tells that you consider the midpoint of both of the end fragments, right? This and this. Then up to this length, this is your final length, right? So the final length is this, and initial length is this plus this plus this one, and eventually the half length of the end fragments. So you take the half lengths of the end fragments, and then whatever the fragments comes in between those two parts, you take them full. So this is the method applied by Hosen, and it is quite more accurate than the Ramses method, because it considers I mean, it eventually cuts off the end part of the in fragments, I mean the half parts of these in fragments. And since we are dealing with the ratio of the lengths, it eventually doesn't matter whether we are considering the full length or not. So considering this, it is much robust method than Ramses method, right? So in this case, the total fragment length is expressed as F total is equal to half summation I is equal to 1 to n. Consider we are taking only n fragment n, because eventually we are cutting off the half of the both ends, so eventually that plus 1 is being eliminated, and then there we write I plus fi plus 1, right? From any end, if you start counting, you take the half of the uh, last fragment. So that is how we calculate the total length of the fragments, and the summation of gap remains the same. G total, it is the same as before, I is equal to 1 to n gi. So this is how we use the Hosen's method, and then eventually the process for calculating the stretch, elongation, and quadratic elongation remains the same. Okay, so this is an overall idea about one dimensional strain analysis using the two commonly used method. So now we will consider the two most important methods for two dimensional strain analysis, because although it is quite easier to use this one dimensional strain analysis method, it is very rare to find these 1D strain markers, right? The deformed fossils or these deformed minerals, right? They are being fragmented and pulled apart. And there are also other several complications in this process, like the we are not considering the deformation of these individual fragments. They can be rotated, right? Even rotation can accommodate the strain. So their angular orientation of these individual fragments, their rheological changes, whether they are suffering or experiencing any kind of ductile deformation or not. So we are not considering all these things. We are simply considering these fragments to be rigid objects, and the material in between, it is a ductile material, and eventually it is being spreading these fragments away from each other, and that from that point of assumption we are making this analysis. So as we, so while these methods are very handy to have an first order estimation of strain, especially in the field, but these are not at all correct procedures. So there are lot of research being dedicated how to actually utilize these one dimensional strain markers to actually estimate the strain. And if you are interested, you can look into papers uh, following the researchers Ramsey, Hussein, and other workers in that area. Okay, so now we will talk about two dimensional strain analysis. So in two dimensional strain analysis, we commonly use two very unique methods. So one is center to center method, which is also known as Fry method, and the other one is RF Phi method. So we will discuss how these methods work and how to use them practically. So this lecture is essentially about to give you a practical idea of strain analysis. You must have, because these are important things, and I took the liberty to discuss these things because these are not in the lecture, and eventually these things will help you to understand how you can perform these in field. Okay. Okay. So first we will discuss about the center to center method. Okay, so now let us go back to another image. Right. So I guess all are seeing this image. Now let us understand this very carefully. So this method of center to center distance, it does not essentially considers the shape of the initial markers. The initial markers can be elliptical, the initial markers can be circular, and of any geometry. If these markers altogether they are not deformed, then a distance from a central reference point to all other centers like this, see, all these distances would remain same or unchanged, right? So if we consider this to be the central reference frame, so from that central reference point, if we consider all the adjacent center points, they will remain same. The average distance would remain the same. So in any direction, right? So in any direction, the average distance would remain same. So in that case, wherever we are measuring the center to center distance, this essentially tells that these are isotropic distribution. Okay, isotropic means along any direction the average value would remain same. So any parameter that we are studying, whether it is a length or any kind of parameter, so the average value of that parameter would remain the same along any direction. Okay, so that is called an isotropic distribution. Now eventually if we deform this entire package of markers, then we see that from center to each and individual points there is a change in distance, right? So if I draw it better, so if this is my central point, I see that, and if this is my this length is my average length, right? So this is my average value, so this much. So considering this much value, so this is the average value. Okay, now along this direction the average value is increased, the average value increased. However, in this direction the average value decreased, right? So there is a preferential distribution of these average values. In some way, in some direction they are higher than the normal, and in some direction they are shorter or lower than the normal. So there is a directional preference that we see. So a directional preference. And in this case we say it as anisotropic distribution. Okay, so the main purpose of this center to center method is that we will have not just one marker, we will have a multiple adjacent markers, so that we will have a statistically larger amount of data, and then we will correlate their distribution of distance. So the fundamental idea is that if the sample is undeformed, then whatever the shape would be, whatever the shape of these individual markers, we should not consider, I mean, talk about the shapes, particularly in this case. So whatever be the shape, if we see that the average distance between one center to the another, okay, along a particular region, if that if that average value remains the same in all those regions, in all over this region, that would say that it is an isotropic distribution. The average distance remains the same. Since if we hence if we observe an isotropic distribution, that would tell us that the sample is undeformed. And in another case, if we see that there is a preferential distribution of these values, in some direction the value is shorter than or lower than the average, and in some direction the value is higher than the average, specifically talking about distances. So if we encounter such an I mean directional preference, then it is easier to say that there is a statistically anisotropic distribution of distances between adjacent points. In that case, we would comment that this particular set of markers are deformed. So this is a very robust method that tells us that if there are no initial preferential orientation of markers, then just by analyzing their distance, center to center distances from a fixed reference point, and then eventually by marking all those distances, if you see that the distribution of distances is anisotropic and it has a preferred direction, then it is definitely deformed, because in undeformed samples the distances between center to center particles or grains or markers, whatever they would be, they would remain the same. So this is an essentially statistical approach. So the center to center method specifically talks about an anti-clustering theory of statistically larger amount of data. So we can say that so this method is based on the anti-clustering of statistically large number of data points. Okay. Now, how to exercise this thing? Again, let us see some photographs. Okay. So we generally apply this method in some deformed samples. So in this case, these are deformed oolites. Deformed oolitic limestone. Okay. So in this deformed limestone, we see these are elliptical shaped oolites. And we have eventually traced all these ellipses, okay, from the photograph, and we use this thing to perform the strain analysis, right? So the first step is what we do is that first we take the traced out image of the strain markers and we need a tracing sheet, butter paper or tracing paper, and eventually the first step would be to mark the center point of the paper as well as the tracing paper. So we first have some reference boundaries. So these are the reference lines. Reference lines are simply the axis, right? So we have these reference lines. Now we place the tracing paper over uh, this entire sheet. Now before doing that, what we do is that we tag or enlist all these different ellipses. So we mark them one, and we do two things. First, mark the center point in this sheet, and then eventually we mark or tag them as different numbers like this. So this numbering can be of any order unless you are messing it up, but it depends on you how you are numbering these different ellipses and so on. So this is how we first mark the center point of this sheet, and then we mark the center of these individual ellipses and tag them with different numbers, right? Now the second part we do is that we place a tracing sheet over these traced images like this. So we have these points, right? So we place the tracing paper over this sheet, right? And the center point of this sheet is, or the center point of the image is being marked in the tracing paper. So what we do is that we take these center point. Okay, so consider this is the center point of the tracing paper. So we take the center point of this tracing paper and place it on the center point of the first ellipse, right? So let me repeat again. We first have this traced out image, and then we mark the center of this image. Then we place a tracing paper over this image, and eventually also trace the center point on the tracing paper. After that, we tag each and every ellipses with different numbers 1, 2, 3, 4 serially, and then we mark the center points of individual ellipses separately. After doing all these things, we place the center position or the central point of the tracing paper on the center point of the first ellipse like this. Okay, so cross, so this cross will be pressed over here, so it would look like this. So we first place the cross over here, and we make sure that the reference lines in the tracing paper as well as the sheet remains parallel, so that there is no angular distortion in the tracing. And once we do that, then on the tracing paper, so if this is our tracing paper, so on that tracing paper we mark the center point of all the ellipses except point 1. So after putting the cross of the tracing paper on the center point of ellipse 1, we would simply trace this point as 2, 3, 4, 5, 6, 7, 8, 9 on the tracing paper, right? So once this is done, we then again move this cross of the tracing paper and place it over the center of the second ellipse, right? And then we will repeat the same process. That means we will simply again plot the center of 1, and then 3, and then 4, and then 5, and 6, 7, 8, 9, 10, and then we will move to the third point and fourth point, and eventually we will iterate the process. That means we have the sheet beneath us, we place the tracing paper over that, and every time we relocate this cross or the central point of this tracing paper to some ellipse, and then we trace the center point of all the other remaining ellipses on the tracing paper. So after completing all these points, eventually we get to see a shape that is popping out on the tracing paper like this. So after tracing all these points, we will see that there is a void space generated around the central point. So this void space is nothing but the strain ellipse. And I was essentially talking about this void space initially. You can see that in this case also we are actually dealing with the spatial distribution of the distances between adjacent points, right? So if there is a directional preference, then the distribution would be anisotropic, and the shape of the area would simply replicate an ellipse. So this exercise is performed like this, and eventually we generate a void space. So this void space is like this. So this void space is the strain ellipse. So once we get the strain ellipse, we can get two information. Sorry. So we can mark this axis and this axis. So this axis would be the maximum stretching direction, and this would be the minimum stretching direction. So this is of course lambda 1, or the maximum or the principal stretch, and this would be lambda 3. So eventually if we know which one is lambda 1 and which one is lambda 3, we can of course mark that this direction is sigma 1 and this direction it is sigma 3. So sigma 1 is the maximum principal stress, and sigma 3 is the minimum principal stress, right? Okay. So is there any question regarding the procedure of calculating the center to center method, or how this is performed? Anyone? Anybody? Any doubt?
No, sir.
Okay. So this exercise is very beautiful, right? Because while you are performing this exercise, initially you would see that you are just blankly plotting some points over the tracing paper and nothing is coming out. So you can see that in the first stage there is nothing. In the second stage it is slowly clustering. So this is the initial clustering, and from that initial clustering we are anti-clustering the data. That means we are creating a void space, right? So the cluster means there are some random points, and anti-clustering means these points are systematically ordered in some way that there is a void space. Complement to that cluster, we are generating this anti-cluster, and in that anti-cluster we can see that the void space generated due to the anisotropic distribution becomes an ellipse. And eventually the main beauty of this method is that this anti-cluster, this void space, the elliptical shape of this void space is actually the strain ellipse that has been I mean the principal strain ellipse of that particular area. And from that we can not only estimate the directions of lambda 1 and lambda 3, that are the maximum and minimum stretching directions, but if the north direction is known, or you have the attitude of the plane along which we are measuring, then eventually you can estimate the direction of minimum shortening, I mean maximum and minimum shortening, and eventually sigma 1, the maximum principal stress, and the minimum principal stress acting or which acted on that particular area, right? So this was the center to center method. Now we will talk about RFI method. Oh, sorry, just a minute, I just switched off my screen. Let me just share it again. Okay. So now we will talk about the, sorry, RF phi method. So RFI method is that, I mean, one of the essential drawbacks, or rather we can say that limitations of the center to center method is that it doesn't consider the fact that even undeformed samples could also have some sort of previous orientation or preferred orientation, especially when dealing with pebbles. In the in the riverbed, pebbles are moderately oriented along a particular direction in the downstream direction and so on. So from that we can, so there are pebble implications, you know, these things in the geomorphology section. You can see that there are certain pebble implications from which we can actually estimate the uh, downstream and upstream direction of the river current, and from that we can estimate the paleo current directions. So in that case, these pebbles were initially oriented, so there was some initial orientation to that pebbles, right? So now if you see lithified and undeformed cross section of a sedimentary basin in a particular strata, you are observing that these pebbles are well oriented along a particular direction, and then you perform this center method, it would obviously generate an anisotropic distribution. Because why? Because there is a preferred orientation, and if there are preferred orientation in along one particular direction, there will be the average distance would be shorter than the other direction, and eventually you will get an ellipse. So but that doesn't mean that ellipse is essentially generated from deformation. So even there can be some anisotropic distribution apart from the deformation. So there is no certain distinction between the undeformed and deformed case, whether I mean when considering the initial orientation of the samples, right? But RFI method deals with the, okay, so I forgot to mention one thing, I should mention it very quickly, that we can not only estimate the direction, but we can also estimate the amount or the magnitude of strain as well, right? So in this case, I forgot to mention that while we have obtained the strain ellipse, so in strain ellipse, so if we measure the long axis, length of the long axis, and we divide it by the length of the short axis, we get R. This is known as the aspect ratio. or it simply is the magnitude of strain in two dimension, right? Okay, so now coming back to the RFI method. So whatever drawbacks we faced during the center to center method, there is another method known as the RFI method. So RF, you can have an idea that since just a minute back I talked about R, which is the aspect ratio. So R most probably will be symbolizing the aspect ratio of the markers. Now what is phi? So phi is the angular orientation of these markers. So the main thing this center to center method doesn't consider is the angular orientation of these different markers. RFI method is also a statistical approach. Center to center method is also a statistical approach, but the difference lies in the consideration of this angular orientation. Because once you consider the angular orientation and measure the statistical distribution, then you can easily eliminate the fact that whether there is any initial orientation, initial preferred orientation of these markers were present or not, right? So RFI method has advantages over the center to center method. Now this advantages being, so this is applicable for initially oriented and elliptical objects, right? Number two is it considers the ellipticity and the angular orientation ellipticity and the angular orientation of each markers. Number C is this method alone, apart from the center to center method, provides an estimation of initial ellipticity. Ellipticity in sense can also be similar to the aspect ratio which we are talking about, right there. Okay, so initial ellipticity and the magnitude of strain. And finally, this is a robust graphical method, and it consider, I mean, it produces less error. Okay, so these are the advantages of this RFI method over the center to center method. Now we will initially discuss about the fundamental theory of RFI method and how it is being done. Okay. Okay. So Consider this as a reference frame, and so we have this circular area, and then we have this elliptical area. Okay, so this is undeformed reference ellipse, right? And this is the initial elliptical object. The ellipticity of this object is Ri. Now Ri is the initial long axis length divided by initial, sorry, not final, initial short axis length, right? So this is the formula through which we can estimate the Ri. Now, what if we deform this entire marker like this? So due to deformation, there will be three changes, right? So I can list these three changes. You can check. So the first thing would be the deformation of the reference ellipse. Deformation of the reference ellipse. The second thing would be the deformation of the marker itself. And the third thing would be the change, the angular change of the line. From theta to phi. So this angle would change, this one. So this angle would change, this ellipse would change, and this strain, I mean this reference ellipse would deform. So eventually we would get a shape like this, right? Okay. So now so now this angle is phi. Previously it was theta, like this. So it has changed to phi. This axis has changed and this has shortened. So this is our strain ellipse now. With ellipticity Rs. So Rs is basically the magnitude of strain. Right? Okay. So, and the final ellipticity of the marker is Rf, right? So once again I am writing this formula. Ellipticity is similar to aspect ratio is calculated length of long axis or major axis, sorry. So length of major axis divided by the length of minor axis or short, right? So therefore we can see that there are several parameters to play with. We have phi, we have theta, we have Ri, we have Rs, and we have Rf. So using all these parameters, the strain parameters, we can actually have an estimation of the amount of strain, right? So to give an idea, we can have some theoretical. So using these two analogies between this graph, this figure and this figure, I mean, that means pre-deformation and post-deformation figure. From comparing those two figures, we can get several formulas such as tan 2 phi. This can be written as 2 Rs times Ri square minus 1 sine 2 theta divided by Ri square plus 1 times Ra square minus 1 plus Ri square minus 1 times Ra square plus times cos of 2 theta. This is equation 1. And eventually we can calculate mathematically Rf as a function of theta comma phi. Sorry. We can write it like this: tan square phi 1 plus Ri square tan square theta minus Ra square tan square theta plus ri square whole divided by rs square tan square phi times tan square theta plus ri square minus 1 plus ri square tan theta, sorry, tan square theta to the power half. This is the second formula. And from the maximum value of phi, the initial ellipticity and the strain can be calculated as, so it is possible to calculate like sine of 2 theta max, sorry, 2 phi max is equal to ri minus 1 by ri divided by rs minus 1 by rs. And then for eventually from this to this, that means the maximum value of aspect ratio at phi max can be calculated as rs plus 1 by rs divided by ri plus 1 by ri plus rs plus 1 by rs divided by ri plus 1 by ri whole square minus 1 to the power half. And by using all this formula, we can have an estimation of numerically maximum and minimum value of RF. That means RF max and RF min, such as RF max is expressed as the product of RS and RI, and RF min, or the minimum value, it can either be the greater value between RI by RS or RS by RI. So whichever value is greater, we will use that one to calculate the minimum value of RF, I mean the final aspect ratio. So these are all boring theoretical estimations. In practical, it can be done in a lot of simpler way. So now we will see that how practically this method is applied to have an estimation of the different, uh, sorry, the different values of initial ellipticity, final ellipticity, as well as the strain amount, right? So consider this image. There are several elliptical objects. So these are the different pebbles which are deformed. So these all ellipses are marked. So we captured. So I took it from the internet. So the task is to capture the image where you are trying to perform this strain analysis. Now, one thing you have to be very sure that you are always capturing a perpendicular view. That means your view should be always perpendicular or orthogonal to the surface. Otherwise, there will be an angular distortion between the photograph and the object. So in that case, it would create a further distortion that would simply uh, produce some error in your data. So what we do is that once we have these markings done, we measure the long axis, sorry, short axis length and the long axis length of each individual marker. So of each individual marker, we measure the long axis length and the short axis length. So we get the readings of whatever data there are, right? Now what we do is that, so consider this is an ellipse. I mean, this is an elliptical marker. Sorry, this should be not, this is not right. Okay, so let me draw it freehand. So consider this as an elliptical marker, right? So this is deformed, whatever it may be. So there is of course a long axis, sorry, so there is a long axis of this marker. What we do is that we consider a horizontal reference frame for each of these markers. So this is a horizontal reference frame, right? And from that we measure the angle between the long axis and this horizontal line clockwise. So phi is the angle between the long axis of the elliptical marker and the horizontal reference measured clockwise. So this is very important to ensure that you are measuring all the data clockwise, because if there is a discrepancy between whether you're measuring clockwise or anti-clockwise, then it would further complicate the analysis, right? So reference measured clockwise. Okay. So you have to tabulate your data like this way. So first of all, you write the serial number of the each deformed marker. Then you measure the long axis. Then you measure the short axis. Then you calculate RF, that is simply LA divided by SA. And then you tabulate your phi. So you measure the data accordingly. So once all this tabulation is done for all these individual markers, we plot the data RF versus phi. So it simply would be like this. So you have one axis, you have another axis, and this plot is essentially plotted like this way. So I'm showing you just a reference. So this is phi in degree, right? And this is the RF. RF doesn't have any unit because it is dimensionless, right? So degree, it would start from 0 to 180. Now once you plot the data, you would see that the data points are clustering like this in a particular range. Depending on how many points you have, so the plotting would generally look like this. Okay. So the task is that you first consider an average value for phi, which is the phi s. This phi s value, okay, the average between this cluster is the orientation or the angular orientation of the strain ellipse. So we can write it like this, that these are the angular orientation of the strain ellipse, right? So once you have this data, now you should observe that where the cluster is lying. So I can see that the cluster is lying here. The dominant cluster. I pick the average value between this dominant cluster and simply extrapolate this value to the x-axis. So whatever average value I am getting, this is RS, which is the ellipticity of the strain ellipse. Now this value of RS is the magnitude of strain in this case. Okay. So you get two information, that is phi s you get here, that gives you the angular orientation of the strain ellipse with respect to that horizontal line you have referenced or referred, and you get the value of RS, which is the ellipticity of the strain ellipse, that in a way tells you the magnitude of strain, right? Now the beauty of this method, RFI method, is that you cannot you just not stop here. Rather, you can have an estimation of the initial electricity of the objects you are studying, because we can apply this formula, right? So from your graphical data, the maximum and the minimum value of the RF can be enlisted, then using either of them we can estimate Ri. How? So if we just use RF max, that would simply be equal to Rs times Ri. Now from the graph we know this, and eventually therefore we get Ri as RF max divided by Rs, right? So through this you can have an estimation of the initial ellipticity of the strain markers, the amount of strain accommodated through those markers, as well as the maximum I mean the angular orientation of individual or the set of markers or the angular orientation of the strain ellipse in that case, right? So now just quickly brief upon the three-dimensional strain analysis, and this part has been elaborately discussed in the lectures itself. So I will just touch upon this thing, is that why do we need three-dimensional analysis? Because all the 2D analysis are conducted over different plane, right? This is obvious because we are observing these features which are 2D or planar features. So of course it is lying along a plane. We are measuring that the attitude of that plane. We are measuring the dip and strike and whatsoever. So in terms of strain ellipse, these planes are demarcated in different ways. Okay. So in terms of strain analysis, these planes are demarcated in different ways. How so? So the first thing is that in field we follow the convention that the direction of maximum elongation is marked as x. So anywhere along the maximum elongation, that would be the x. Perpendicular to x, the intermediate value is y, and the minimum value is z, right? So this is how we define different planes while conducting the three-dimensional strain analysis. Now you have to think very carefully that three-dimension analysis is done by parts having two-dimensional analysis in different planes, and then we assemble the data together to have a three-dimensional interpretation. But all the measurements are strictly done, I mean sensu stricto to two-dimensional analysis. So therefore understanding the two-dimensional analysis is very important, because we just perform the 2D analysis in three different planes and then we assemble the data to have an estimation of the three-dimensional case, right? Because eventually all these objects, whether it is a deformed fossil or deformed pebble or whatever it is, these objects are essentially three dimensional. Hence, only we are since we are observing only along a preferential outcrop, that is a plane, we have to continue the study or to iterate the process in three different planes of mutually perpendicular orientation to have an estimation of the three-dimensional strain distribution of a region, right? So if we just consider this like this, so this obviously would be x, this is z, and this is y. So here we have this xy plane, we have here this is the xz plane, and like this here we have this yz plane. Okay, so in each of these plane, the strain analysis, the the 2D strain analysis rather, is carried out separately, and then the data are plotted in the Flynn diagram, right? So how it is being plotted in the Flynn diagram? Now in two dimension we are measuring the aspect ratios in uh, only by one parameter, right? So either it is r, uh, either it is r denoted by the long axis divided by short axis. In this case we measure it, right? But in three dimension we need two r, right? Two aspect ratios in different planes. So how is it classified? So in 3D the aspect ratios are measured in two categories. So one is R12, which is expressed as length along x divided by length along y, and number 2 is R23, which is length along y divided by length along z. Okay, so using these two parameters we calculate k value, which is defined as R12 minus 1 divided by R23 minus 1. Okay, so this is how k is calculated. Now there are several ranges of k, and we observe these different ranges in the Flynn diagram. So if I just draw a hypothetical Flynn diagram, so in that case the R12 is plotted along y, I mean y axis, not capital Y, and R23 is plotted along x axis, right? So this is another beauty of, we call it as dimension reduction, right? So dimension reduction means we are combining the different r values together in such a way that we get only one parameter that can be plotted in a two-dimensional plot. So eventually there are three types of r values, right? Along one, I mean along each along different axes, x and y and z differently. But we are combining these values in such a way that we do not have to plot all those things in a three-dimensional diagram. Instead, we are projecting the entire mathematical formulation on a two-dimensional space. So this is a mathematical operation we generally refer to as dimensional reduction. And since this case we are applying this, I mean we are performing this plotting where R12 is plotted along y and R23 is plotted along x. And mathematically we can draw a 45-degree line like this, which is represented as plane strain condition. Okay, so plane strain condition means there will be no deformation along y axis. All the deformation would be constrained along x and z direction only. So that is called plane strain condition. And in this case, k value is 1. Along this axis, we plot ln x by y, and along this axis we can plot ln y by z, natural log of y by z. And you can see that this entire thing is divided into two different domains, right? So this is one domain and this is another domain. So of course there are several values of k boundary conditions. So in this case k is equal to infinity, and in this case k is equal to 0, and here k is equal to 1. So depending upon the different values of k, we can have k is equal to infinity. This symbolizes x far greater than y, which is greater equal to z, and this essentially indicates axially symmetric stretching. Okay, the second is k is less than infinity, but this is greater than 1. So it is generally, in this case x is greater than y, but y is equal to z. This is known as constrictional strain, or we can say that cigar shape ellipse ellipsoid, which is known as prolate. Then of course we have k is equal to 1, right? Plane strain condition. And then finally we have this, not finally, we'll have this k value less than 1, but it is also greater than 0. This is known as flattening strain. So in this case, so in this case we will have x greater equal to y greater than z. This is known as the flattening strain. And this is this domain, It is also known as pancake shape ellipsoid, or oblate. And finally we will have k equal to 0, right? So this condition is represented as x greater than y, which is far 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 greater than z, and this represents axially symmetric flattening. So the exercise is simple. You carry out the strain analysis, two-dimensional strain analysis, measuring the long axis and short axis whatsoever, and measuring the aspect ratio of the deformed markers. And then you simply iterate the process in three different planes, mutually perpendicular planes, and you calculate natural log of x by y and natural log of y by z, and simply plot on the Flynn diagram. And depending on the position of the points, you can easily segregate whether they are falling in the prolate shape or the oblate shape. And from that you can estimate, you can have an estimation of the value of k, and that would tell you that what kind of deformation it is, whether it is constrictional strain, whether it is uh, flattening strain, whether it is axially symmetric stretching or axially symmetric flattening or plane strain condition whatsoever. Okay, so this is how we perform 1D, 2D and 3D strain analysis, particularly obtained from the field data. So this was a short discussion over all the topics of strain analysis. So if anyone has any question, please ask quickly. I can answer one or two questions, or else I will close the discussion. So any question? Okay, so if there are no questions, then I am stopping this discussion session, and we will meet again next week this time. Thank you.